We are on page 59. All right, page 59.
Right next to each other.
All right, page 59. So to motivate this, it's hard to study something if you don't have a reason to care.
Don't care.
Okay, that's cool. I think we're not past the drop deadline. It's cool.
Someone had to say it.
Well, maybe this will help. I don't know if it will. Let me get that. All right. So we're going to be talking about moment of inertia, which is the symbol I. Now there's two things coming up that we use it for: torque and rotational kinetic energy. If it helps to understand where this is related, you might remember something like force equals MA. Or perhaps you know about translational kinetic energy. What was the equation for kinetic energy for a particle moving around? You remember?
1/2.
And I want you to notice, basically, I, or moment of inertia, is the rotational equivalent of mass. Now, you're not always going to hear this, but sometimes you'll even hear me say rotational mass. That's not a physics term, it's not an engineering term, but sometimes, if it helps you to kind of get a feel for it, it's the rotational equivalent of mass. All right? So if we want to know how to do torque problems or energy problems for things that rotate, we need to understand this new concept, moment of inertia. That's one. So hopefully, maybe you're not excited about it itself, but maybe you can see the reasons why we might want to care. Any questions about that? All right. So if you look at the top of page 59, there's a one statement in bold. Compared to mass, moment of inertia is a world of pain. Okay, it just is tougher. Mass is just a number. You put something on a balance and you get the mass. Moment of inertia is very different. Maybe I'll just emphasize it like this. So let's just say I have this arrow here, right? You put it on a scale, you get its mass. Its moment of inertia would depend on whether you twist it like this, or like this, or like this. It depends on the axis, the orientation, and the distribution of mass. Two objects can have the same mass, but have different moments of inertia, different rotational mass. The four factors that affect it are listed there, and let's try and say the same things I said there. Remember, I is the symbol for moment of inertia. The amount of mass, so basically the weight divided by g. The shape, or mass distribution, the axis location, axis being where you plan to rotate the object, and axis orientation. Basically, it depends on which way the axis is pointing where the axis is located relative to the object, how the mass is spread out, etc., and the amount of mass. If you look on page 59 in your book, you're going to get a table looking. I copy that table and put that set of pictures there. You see the pictures with the basketball and the cylinders and the discs and things on your book? That's going to be given to you on your equation sheet on test day, so you know. So you're going to, right, it's so complicated. There's so many formulas. Most of the time, we are able to look at this page, grab a formula, and use it. But notice, maybe I'll just emphasize two of these. Here's the axis through the center of a plate. Here's an axis through the center of a plate. So the dotted line is, in this case, the axis. Here's an axis. And this is just a rectangular plate. And if you look in there, I believe they're the third column. We see that this one, and let me get the dimensions right. I think I said this was A, and this was B. This has a moment of inertia of 1/12 mass times B squared. Okay? Whereas this one, also with dimension A and B, figure not to scale, axis through the center, this one ends up being, what is it? 1/12 mb squared plus a squared. These are very different formulas. We can see that it's important in a problem to identify, most crucially, the axis orientation. That's what I'm trying to show you right here. In both cases, the axis is located at the center of the object. The axis runs through the center. But the orientation of the axis, one's about the z-axis and one's in plane, about the y-axis, say, we see you get different moment of inertia. You can see that here's a dependence on the shape. Some of the dimensions factor in and the mass. All right? So far, so good? When you're looking at a picture, make sure you grab the right one. That's what I'm trying to say right now. A lot of times they look similar just because you get a plate or a rod. Look at the rod. Second column. 1/3 versus 1/12. Right? If the axis is through the center, you use 1/12. If it's through the edge, you use 1/3. That shows up in a ton of physics problems. All right. Let me get a demonstration. Go ahead, you can pass these around. Yeah, question?
So if the second one,
Uh-huh.
the one that wants 1/12 mb squared, if it was like rotated, like you rotate like
If you put it this way, what would the moment of inertia be?
1b a squared.
1/12 m
Well,
a
yeah,
squared. Yes, absolutely.
Okay.
And so that's the thing. Some of these you have to think a little bit. You're like, well, a rectangle shouldn't matter if I flip it. All that does is basically flip A and B, right? Yeah. So we've got these two rods here. They have the same mass. All right. I'm going to pass them around in a minute. Although I want to notice something here. I don't know if you can see that, but at the ends, one of them, you can see the mass is at the end. This one, the blue one. And then if you look at the center, this one has no mass at the center. So it's the same mass rod, only this one has a couple of point masses at the center, and this one has some point masses at the end. And I'm going to pass these around. Try just grabbing them at the center and rotating them. Got it? Let's get a feel for that. If you're curious, this is modeled in problem 10.8. So if you want to look at 10.8 really quick, we can talk about it while those are going around the room.
The red one probably there for blocking. You thought
The red one's better for blocking, this one would be better for. Like how we got this fighting. Rotate. That's why you don't get me sticks.
You try switching hands to make sure they feel about the same. You're gonna have an axis of rotation here about the center. All right. And so as those are going around, you can really feel the difference, right? Which one is easier to rotate in this case?
the red one.
Yeah, which on the screen, on the whiteboard here, which one is that? Masses at the center or masses towards the end? Which one was easier to rotate? Center. So what do you think that tells us about the I for each of these? I is like its rotational mass. Which one was easier to rotate? Which one has a bigger rotational mass? One. The one that's harder to rotate, you can feel it having more rotational equivalent of mass, more moment of inertia. Now, in general, what happens in a physics problem a lot of times, or an engineering problem, is we try and take an object and build up the total moment of inertia out of the pieces. So let's work through this together. I'm going to do this first one. In this case, the moment of inertia for object one is going to be the moment of inertia of this cylindrical shell, the plastic. Can I have one of those back? All right. Yeah, exactly. Oh, I need the blue one. Sorry. This is the one that has the point masses at the end, right? You can see the hole right there. Hopefully you can see the whiteboard through there. So in this case, right, there's this plastic shell, which basically is like a thin cylinder, and then a cylindrical shell, and then there's the 2 point masses at the end. So what I'm going to do is I'm going to try and look in the table and try and figure out which moment of inertias apply. Well, when I look at this one, even though it may not seem like it, let's see. In this case, what am I going to do with the cylindrical shell? We're going to treat, oh, it's a rod. We're going to treat it as a rod. Okay, so in this case, we're going to treat it as a rod. All right, trying to follow the example in the book. So in this case, what moment of inertia should I use for the plastic rod? Do you think it's 1/3 ml or 1/12? Look at the pictures and which one does it look most like? 1/12. It's at the center. Take a look carefully at those pictures again. The 1/3, the axis is at the end. The 1/12 is at the center. So we're going to say this is a 1/12 mass of the rod times length of the rod squared. Now I have these 2 point masses. Does anybody see the formula for a point mass in there?
MX squared.
Mx squared. So I'm going to say mass of the point mass times x squared. In this case, we were given some dimensions here. So the pipe, or whatever the plastic, has mass m and length is L. Oh, it's just L. The point masses they have mass, what was it, 5m? All right. And their radius is the total length over 25. So they're very small compared to the rod. That's why we're able to treat them as a point mass. So the whole point of this is just saying, look, these objects are 25 times smaller than the rod itself. We're treating them as point masses. Obviously, they are not point masses. We're treating them as point masses. We're assuming they're small compared to the rod, and that's why it's okay. More on that later. At this point, we could shove in some stuff, simplify the fractions, and get it. Let's do it real quick. Race me. 112. Oh, what's x? For this problem, what's x? What does x mean in this formula?
Distance from the axis.
Distance from the axis. Yes. So what is x in this case? What is it? L over 2. Yes. And then you got to remember to square it.
Not L over 50.
What's that?
Not L over 50.
No, no. So remember, look at the picture on the page 59 there, if you can. That's all right. Just look behind you there. Look at his book. See how the picture X means, and that's why it's critical to understand this chart. X means distance from the axis, not the size of it. Got it? All right. And so that was one of the things here. It turns out this was decoy information until you get to part C or something. All right. Now in this case, we could punch in a bunch of numbers here. Oh my gosh, I'm running out of room. Let's keep going up here. When we square that, you got to remember, okay, so I got a 10m there, let's split over 4. 2 came from the fact that there were 2 point masses, both distance x away. X was L over 2 for both of these. Nice. What's that going to be? You could just go to, whoops, L squared. Is that right? You could just go to a, whoops, ML squared. You could go to a calculator here, I guess, or since we're close. What is that? 30 plus. To be fair, it's probably easier to go to a calculator, so just do it. But if you, I have a tendency to do fractions for these problems. I don't know why. It's just how I grew up. All right, so far so good. Well, something that we usually do when we're first learning about a topic is we check the units. We haven't discussed this yet, but can you tell what the units should be? What are the units of moment of inertia? What are the units of mass? What are the units of length squared? Kilogram meters squared. So those are going to be the units. You're always going to have some kind of mass and some kind of distance squared. All right. So far, so good. Let's try this one. It's a little bit easier. It's still the same mass. We still have 2 pieces. We still have the rod, and we have 2 point masses. In this case, what is x approximately? What happens to I of the point masses? Drops out. So notice I2 is a lot faster. It's just going to be 1/12 ml squared. Now, if we have a calculator, I say it's worth it. What's 1/12 approximately? 0.0833. Is that right? Making sure I don't screw it up. Is that right?
Yeah.
What's 31/12? Can you help me out with that one? I don't have that right there.
That one's
2.58?
Yeah.
3? All right, whatever. Do you agree the moment of inertia of 1 is huge compared to the moment of inertia of 2? They have the same mass, but it's so much easier to rotate this object when the mass is in the middle. Now, I know we haven't talked about angular momentum yet. We will. That's chapter 11. You probably know about the figure skater, arms out versus arms in, right? This is kind of a model for that. Model a figure skater as a rod. Well, never mind. Okay, let's just say figure skater arms out. Is the moment of inertia big or small? Let's do it that way. Big, small. Which one is easy to rotate quickly? Small. So that's why when they bring their arms in, they start with their arms out, and then they bring their arms in, they conserve angular momentum. Next chapter, we'll worry about it then. But if the figure skater analogy helps, arms out, slow rotation, big moment of inertia. Arms in, fast rotation, small moment of inertia. Okay. Obviously, you could make big things rotate quickly too. Neutron stars or something like that. Pulsars make me think of that. All right. If you're curious, look at 10.9 right now. Same problem. We don't have time to do it all, but we're just going to change the axis location. Same two rods. Same 2-point masses, only now the axis is here. At the end, which one do you think has the smaller moment of inertia? I want a smaller moment of inertia this time. Take a guess. Do you agree the rod itself is pretty negligible? Right, that's what we just saw. The rod itself is pretty negligible compared to the point masses.
Are they the same?
Oh, I don't know. What's the moment of inertia for just this point mass? Give me an equation.
ml squared.
That's the moment of inertia of this point mass. What's the moment of inertia of this point mass? So do you agree the moment of inertia of this thing is not going to be exactly this, but it's pretty close to ml squared. There's a small contribution from the rod. Oh wait, it was 5m L squared, wasn't it? Because those point masses were 5m,
Yeah.
right? What's this mass? 10m. What's the distance?
L squared over 2.
No, L over 2 quantity squared. Which, do you see the subtle difference?
Mm-hmm.
What happens?
2 divided by 10. That's the same.
You get 2 of them, right?
Yeah.
It's smaller. So notice the bigger contributor here is not the amount of mass, but it's the distance because that's squared in the formula, right? So you're saying, oh, one of these versus 2 of those. Yeah, but the length gets squared. And so grab them, rotate them about the end like this. Oh my gosh. Try it. You guys got it. Do it. Try both of them at the end. Switch arms. All right. Isn't that cool?
Is this how lightsabers work?
Pretty much. You put a flashlight inside, you're good to go.
Not much.
No. Do you agree they're certainly much closer than they were before?
Yeah.
Before, the factor was about what? Oh my gosh, 40 times different. Now the factor is within a factor of 2. And what's a factor of 2 amongst friends? Come on. But yeah, so isn't that interesting?
It's like swimming at the
As a diver, you probably know all about moment of inertia physically, right? When you do spins, right?
Oh.
It's the same concept,
Yeah,
right?
you're
You
trying
go
to-
into a ball, so
you're
you
trying
get versus a pike versus etc. And now I better shut up because I don't know anything, and I better stay out of it. But right, if you think about it, I hope you don't think about it while you're diving, right? Hopefully,
No, yeah.
right?
The idea is to bring yourself as tight as you can into a
Which
ball.
reduces your moment of inertia, which allows you to get a higher rotation rate, so you can actually complete more spins
You then
before hitting.
transfer into the wall, which launches you out.
Oh, okay, yeah. So there, yeah. So we can talk about it afterwards. That'd be cool because I don't know. I mean, I haven't thought about it, but I know it's obviously related, right? That's all I know.
Yeah.
Any chemists in here? Any chemists? All right. Well, I wanted to mention 10.10. Just finally, look at 10.10 really quick. And just so I have it all on one whiteboard. Oops. So let me just mention this, 10.9. Now, to be clear, we didn't finish this problem exactly. We're just getting a feel for it. But I think that's what's more important at this stage. If you wanted to go back and do the actual calculations, you could. And 10.10, I feel this really illuminates the issues involved with moment of inertia. What if we put the axis this way? Right? Which one? Whoops. They're the same. They're exactly the same. You're right. I screwed up. One of them's got to have the masses at the middle, doesn't it?
We just solve physics,
That's right. But you know what's funny?
not physics.
They're still the same.
They're still the same. Right? Because about this axis, try it, grab them, twist them this way, right? The idea is the masses have the same distance from the axis. This cylinder's on axis, this cylinder's on axis, the rod's on axis, same for this one. And so now this is a different, it's more, we can no longer treat these objects as point masses because their size is no longer negligible compared to their distance from the axis. So in this case, now, I don't know if you can see this, but the reason I asked about chemistry is you can think about an oxygen molecule, right, as two atoms connected by some force. Obviously, they're not connected by a spring, but in this case, we'll model it that way. And think about it. You could be rotating this thing about this axis, or maybe even an axis out of the page. And the rotational energy associated with this molecule spinning will depend on the axis you choose.
What about diagonally?
Oh, you could rotate it that way too. Yeah, you could rotate it anywhere, but I'm thinking about the three principal axes right now. So if you wanted to rotate off that, usually you do a complicated process that I'll say for that guy back there. He can tell you about what happens when you're going to rotate about weird, and usually you get matrices involved and then diagonalize the matrix or something. But I'll leave it for Dom to tell you about that after class. How about that? So, but for right now, it's easiest to think about the rotational energy spectrum of chemistry actually depends on these moment of inertia differences. And you can see that, well, one of these moments of inertia is very small. Do you agree this moment of inertia is going to be very small? The mass is all close to the axis. Remember that. Mass close to axis, moment of inertia small. Got it? Small moment of inertia, big moment of inertia. All right. You could go back and do those if you want with numbers or anything you want, but I think that's good enough. Let's go to page 60. Go to page 60.
What if there's only one weight on the first rod? How does that change things?
Which problem are you talking about? 10.8, 9, or 10?
Just for, if you just have one mass on rod one.
One mass on rod 1. So where would that affect this calculation? Right there. Now, to be clear, there's a serious issue when you take one of the masses away. It's no longer balanced. And then as it rotates, you're going to be raising and lowering its center of mass, right? Right now, the center of mass is right at the center. So that makes it easier to balance. And that would change how basically the torque your hands are going to have to exert while you hold it.
Are we only going to be working with balanced?
No.
No.
No. But for right now, I just like this one because that's what we have right there. And so these ones are balanced so that you can get a feel for it, hopefully not injure yourself too often. As somebody bonks their head. Is that good?
Yeah.
So certainly, we have to start with the basics, right? I could go full bore and everyone would fail completely. We're already having trouble with that, so maybe we should stick to the basics for now, right? Yeah, we're gonna build this up over semesters. Yeah. Take a look at page 60. Will I erase the board, everybody? Page 60. Will I erase the board?
You have to really pull this out.
Dom, while I'm erasing, is there anything you want to mention about moment of inertia that jumps out in your mind? Obviously, we got a ways to go, but
No, but we just covered this in my class last week.
when you're doing it, you do a lot of matrix stuff, don't you? No? Oh, maybe that's advanced mechanics or
That's the
something.
next one.
Okay, that's the one active.
Don't scare me.
Now, I tend to avoid the perpendicular axis theorem. I briefly cover it. Do you actually use that? No. I do use the parallel axis theorem a lot. I'm sure you do too, right? So I try not to make the calculus problems that significant. In particular, I usually, if I'm going to do a calculus problem with moment of inertia, which that's the page you're looking at on page 60, I tend to focus on thin rods. I don't think I've ever given a test question on moment of inertia with calculus that wasn't a thin rod. So put a star next to that on that chart, people. Page 60, star next to the thin rod. That's the one you got to know how to do for this class. I show you the others for completeness, but just wanted to kind of give you a heads up right now. We don't tend to focus on those others. That said, usually there's somebody that asks the question at some point, like, how do you get these formulas? That shows you how to get them. So if you were wondering how these formulas are derived, that sort of gives you an idea. Okay. In general, the classic way to get these with calculus, it's a little different than center of mass. I'm just going to show you this way. I is equal to the integral of di, right? And you might say, wait, isn't it delta I? Shh, I didn't hear that. I want to get through this. Again, we're trying to focus on what you need, so just let me get through it. If you care about why there's no delta, I'll explain it in office hours or something. What you could do is you could take an arbitrary object and build this thing up. Let's say you have an axis of rotation. You could build this object up out of cylinders. But this is getting pretty complicated, as you can see. you try and build this object up out of these cylinders, and they're actually thin cylindrical shells.
We're using the shell method.
Yes.
Well, you gotta invite these guys too.
Well, remember, you're not going to have to do this in my class. So I'm just trying to show you the basic principles. In theory, there's a radius in the calculation. The radius is the distance from the axis. In theory, you could build something up out of cylindrical shells in calculus class. In practice, what happens if we take this to a rod? And here's our axis. The trick is, right, you can imagine having the same cylinder here. Right? And then what's going to happen is this cylinder, the only piece that matters is right here or right here, right? And so what we do is we cheat the system and we say, well, instead of doing this integral, all I have to do is add up all the mass chunks. So I'm going to erase the cylinder completely. This is a good time to have that ghosting. So this is actually a distance x. The thickness here is dx. What's dm from calculus or from center of mass calculations for a one-dimensional object that looks like this? Lambda dx. So our integral becomes, we take this, oh, and notice x was the radius. That's the radius from the pivot point or the axis. In this case, now I beat the crap out of you guys on one-dimensional calculus center mass so that hopefully this is like, okay, I could do that. You just plug in some crap and go, right? The only difference is there's no denominator, and instead of an x, you have an x squared.
What about finding initial finding?
So in this case, let's say this was negative d, and this looks like it's about positive 2d. I don't know, just from my angle on the board, I can't tell. What would be your limits? Don't overthink it. What's the leftmost value that x can take? What's the rightmost? Done.
So you're taking the entire rod into account?
Exactly. And notice, that's going to take care of any minus signs. You see what I'm saying? So, and just like in here, right, it's the distance that matters. And so remember, it's distance squared in the moment of inertia all the time, distance squared, distance squared. So we didn't care if it was above or below in that first problem. Remember that? Yeah, so because it's that distance squared, sweet. Is that good? Yep, question?
That's not the next, right?
Oh, that's lambda dx. Thank you. I was trying to do too much at once. My bad. This right here is lambda dx. Yes, thank you for correcting me. And so, like I said, we're not going to be putting 2D on the test. If you need to understand some of the problems that have 2D, great. There's instructions in the workbook. I guess I will mention plates. Sometimes we talk about plates. Plates are very common in this class, so those are probably worth discussing. Let's go over to the other whiteboard and talk about a plate. And you can see that there. This triangular one is kind of interesting. Where did I put that? Okay. Well, let's say we have a triangular plate here. It turns out the same concept can apply here. You can slice this thing into chunks that are parallel to the axis. So I'm going to say that, slice parallel to axis. And then when we do that, what's a good name for this distance, assuming we use a standard coordinate system? X. What's a good name for this small size of this chunk? Okay, dm is the mass size of it.
Yeah.
The dimension would be dx, and how do they relate in this case? Well, we got to be careful. This is now a 2D object. This should technically be sigma dA. We need a 2D density, right? But what is dA? You remember when we did the triangle center mass problem? It's an area, right? Pretend this is a rectangle. What's the height of it? What would be a good name for the height of it? Okay, is the height a constant? I would call it y dx, where y is the value of this function. You know what I'm saying? Y can change. And so then this now looks, dx would be the width of it, height times width times the density, you get a mass. All right. So far, so good?
What does the integral look like?
Why don't we just do it? Take a look. This is problem 10.13. We're going to use this result sometime, so it's not bad to do this one. And again, this might not be used on a test, but because this is used in some other problems, maybe we should do this one. 10.13, we're doing it. Okay. Except this time, let's draw the axes in a normal way so that we don't have to get confused. Let's actually draw coordinate axes. Let's start simple and put the corner right there. And then we're told that this dimension is A, and this dimension is B. Now, because this picture down low is different than that one up top, I want to erase this picture up top so that we don't have two conflicting axes and stuff. You okay with that? So we're just going to actually do the triangle slowly. That way you understand it. Mass M. And then we're going to rotate it about what axis? Does it say? Oh, the vertical axis. So let's say X and Y, and we're going to rotate about Y axis. Okay. Now in this case, let's slice it up. If we're going to rotate it about the y-axis, do I want horizontal slices or vertical slices? No. You want to slice parallel to the axis for these problems. So remember, when you wanted a y center of mass, you sliced it horizontally. When you want a y moment of inertia, we slice it y. So that's a confusing point. I'll say it again. If we wanted to get the y coordinate of the center mass, we usually slice it horizontally. If we want to get the moment of inertia, you slice parallel to the axis. That's a subtle difference. Everybody got that? Maybe at the end of this, we'll summarize some of these things that we learned. Okay. All right. So in this case, I want to slice this way. Why do I have to slice this way? It comes from that imaginary cylinder. Remember that? You're having a cylinder wrapping around this thing, an imaginary cylinder in space that has some radius. And that's why we want to slice it. Every point in this slice is equidistant from the axis. When I write down the equation, I equals r squared dm. If I want to do this, every piece in the slice needs to have the same distance from the axis. So let's write that down. Is that helping you get that? You feel better on that now? So the trick is, if you're going to use calculus, you have to make sure the math formula that you have memorized actually applies. It only applies if all points in slice equidistant. I'll get out of the way in a sec. Is that better? Just having it all written. Gosh, wouldn't this be easier to code? Too soon? My bad. At some point you realize, wait a minute, it probably is. Or plug it into Wolfram Alpha. But then you got to know how to use Wolfram Alpha correctly. A non-trivial task. That dimension is dx, this is x. We're slicing this thing up. Let's go ahead and write this down. Well, in this case, what is the distance from the axis I should use? How far is this slice from the y-axis? X. So instead of writing r, I can write x for this problem. dm. In this case, 2D object, dm equals sigma dA. What is sigma? What does it mean?
Density.
What kind of density? What units? Kilograms per meter squared. How do I get sigma for a uniform triangle? This was uniform. Remember how to get sigma?
Mass times dm.
No, I meant, like, let's say something has a mass of 2 kilograms and it's, you know, its dimensions. How would you get the mass density? How many kilograms per meter squared? What would you do with the mass and the dimensions?
Total mass.
Total mass over total area. Now, you're right that it also relates to dm over dA, but it also relates to m total over a total. And this is something that's easy to compute compared to the other one. So it's not that what you said was wrong, it's just we want to know this, plug it into there, so we can plug it into there rather than try to work backwards. In this case, the mass was m. What's the total area? One half AB. So can I clean that up? 2m over AB in this problem. All right. Now I know sigma. What's dA? dA means area of my slice. Well, that's going to equal slice height times slice width. Right? It's a rectangle, approximately. What's a good name for the slice height in this picture? That would only be the height of this slice. That would not be the height of this slice or that slice or this slice. It's not the slope, but it relates to the slope.
ADX.
I would say it's the height of this line. Agreed?
So the function.
The function. What's a good name for the function? Slope x plus intercept. It's a line, right? Does that, remember this from when we did it a week ago? Yeah, and then we want to avoid m because we already have an m, and so I called it slope. Yep. All right. What's the slice width?
Yeah.
dx. From here, do you see how to do the rest of the problem? What's the slope? What's the intercept? Turn the crank. I'll race you. I'll go slow. What's the slope? Rise is negative a over b is the run. The intercept is a dx. Before going on, I always check. When x equals 0, I get the correct height, a. When x equals b, I get 0, also the correct height. Because the function works at 2 points and it's a line, I'm good. I plug in some crap. I'm gonna sneak in that sigma. Maybe I'll make that sigma a different color right here so it sticks out. So, right, it's not just the dx's. You would check the units at the end and it would help you see if you forgot the sigma. I could pull out some constants. What 2 constants can I pull out? What 2 constants can I pull out? X is not a constant. X is changing as you move through the triangle. A is, what else? Uniform, what does that tell us is constant? Sigma is constant. I better color code this too. So I'll pull out a sigma A. And I get negative x cubed over b plus x squared dx. Jacob, what limits? What do you think? 0 to b. Exactly. You feeling good on that now? The smallest value x can take is 0. The largest value it can take is b. Nice job. All right. What's something you could do if you were worried you screwed up? What could you check at this stage to make sure you're feeling a little more comfortable? We could check the units right here. Well, I'm just going to check at least that these 2 units are the same. I'm not going to check everything, but meters cubed over meters plus meters squared. Okay, I at least feel good that the complicated part has the right units. And then, oh boy, so yeah, there's a bunch of other units in here. Well, let's do it. What the hell? We got kilograms per meter squared times a meter. Both of these are what? Meter squared? What's dx? Does it have units or not? Meters. It's a tiny distance, but it's still a distance. Nanometers are still a small amount of meters. Geez, what do you get out of all that? Kilogram meters squared, that seems like a strange unit. I-80. That's okay. That's what we're doing, right? Kilogram meter squared. Feeling good? And then I'm worried about running out of room here on the Zoom camera. It's like right at the edge, so let me do this. Let's give myself a little headroom here. Let's go right there. I got some room. Okay. Now I'm going to erase that crap. That was just for me to check it. I'm going to erase it now. I was just checking the units. another board space. So out of here, I get I. Let's see, what do I get on the first term? What does that become? When you integrate negative x cubed over b, what do you get?
Negative x to the fourth x over b.
Negative x to the fourth over 4b. And that one should be what? X cubed over 3. Evaluated at 0 and b. We should always check the 0 limit. In this problem, do I need to worry about it? No. The 0 is going to drop out. Here I took the liberty of canceling one of the b's, right? I get b to the fourth over b. Negative 1/4 plus 1/3. What are you going to do with that? That's a common trick. Common denominator. 4 minus 3 is 1/12. Note to self, if you're struggling on a test, write either 1/3 or 1/12. For some reason, they always turn out 1/12 or 1/3. Just a side note, right? If you're completely lost, write it down and see if I don't notice. Oh, jeez. Telling you all the tricks. This looks great. But we should probably put this in terms of mass, so it looks like every other moment of inertia in the table. Mass and distance. How do I get mass in there? Maybe I'll keep this color coded. What was sigma? Oh, the trick I told you is going to fail. It ends up being 1/6. Out of all that, what do we get? One of the A's drops. Well, the only A drops. One of the B's drops. And we get 1/6. All right, you asked, do you feel like you could do moment of inertia for a plate now? Maybe with practice you could. You do 2 more of these, you'd be automatic, right? I have a fun question for you when we get this done. Get it up here when we get it right. What if we have this triangle, and I think I've got it over here somewhere. Like this. Okay. What if I rotate it this way versus this way? They got the same mass, the same dimensions. It's a triangle. What should be true about the moment of inertias? They're different, good. So that's the subtlety about this, right? Every single problem you gotta think. Which is of course why I love moment of inertia and why students sometimes go insane dealing with it. Every problem requires thought. In fact, here's a cool trick. If you wanted to go back, look at the problem 10.12. If you look at 10.12, 10.12 uses a rectangle. In theory, what you could do is you could say the rectangle is equal to this triangle plus that triangle. If you knew the result from a rectangle, if you had already done problem 10.12, which we usually do in that order, but I didn't this time, you could actually figure out the moment of inertia of this one by saying it's the moment of inertia of this minus that portion. So you could do basically a rectangle with a triangular hole. So all of our center of mass traits where you could subtract moments of inertia for holes also work. Isn't that cool? I think it's cool. All right. This is probably a good time for a break. Let's take a break right now. All right. So good job. Hey, Zach, can you hear me? I might be. Yeah, you're on mute. Oh, he's just. Oh yeah, man, that binary OR operator, the straight line, far out, man. We'll have to talk about that tomorrow in lab, eh? I thought that was an interesting way to do it. For that center mass code, the circle with the hole in it. Remember, you used to. Anyways, I thought that was a neat way to do it. Okay, let's get back to it. All right, so let's see where we're at here. I'm going to look at 10.14 really quick. I'd rather do it or at least start it. So this is a problem that is more typical of exam type difficulty. So that's why I want to at least kind of go through it. So basically on a test, I'm going to ask you a moment of inertia question, guaranteed. Guaranteed. I'm going to ask you something about rotational kinematics from last time, guaranteed. Right? And then the types of questions that I asked, you saw the types of questions I asked for rotational kinematics last time. The types of questions I like to ask for moment of inertia are either build something out of shapes like that first problem that we did where you have to add multiple pieces together, or calculus on a 1D rod generally. So let's do this. And let's assume it's kind of got a variable density. All right. Okay, and so we're told rod length equals L, density is lambda equals alpha x squared. So you can tell by the shading, or at least my attempt, hopefully that makes it clear. It's more dense at this end. Look at it. If this is our coordinate system, as x gets bigger, the rod should get more dense. You might say this is never going to happen in the real world. Well, what about something in like a centrifuge, right? In something in a centrifuge, you might expect the density to increase as you go outwards. And so maybe we need to understand the rotational energy of this thing. So this is not an entirely out of nowhere idea here. It's quite possible we might have rotating objects with variable density. Okay. Total mass is m, alpha is unknown. Rotated about y-axis. Right? Okay. I'm going to put a note here. Does anybody know the moment of inertia of a uniform thin rod of mass m and length L about this axis? From the table. (1/12) or 1/3? So if it was uniform, the answer would be 1/3. Do you expect our answer to be bigger than, less than, or equal to 1/3 ml squared? What's that? Why? You have the same mass, same total mass. On average, more of the mass is farther from the axis. We expect it should be bigger than 1/3. Is that good? And maybe that's what you meant, more mass farther away.
Yes.
Okay, gotcha. So more of the mass is farther away. Here, it's off, right? It's spread out evenly. Here, more of it is far away. Good. So we expect our number should be bigger than a third. That's our check. All right. Nice job. Total mass. This shows up on a lot of test questions, and I've seen some people stumbling on this. Oh, so A, we expect I greater than 1/3 ml squared. That's what we just discussed. B, mass equals the integral of dm. I want that to be second nature to you. This should be second nature, right? If you're wondering why it's not a delta m, well, the initial mass of nothing integrated is 0, right? So it is a delta m. It's just m minus no mass, which is m. In this case, we've seen this a lot. This happens in center of mass. This was the denom in our code. Remember the denominator, right? If you need mass on a test question, just integrate dm if you see something like this. It's not supposed to be, you're supposed to know that. Well, in this case, what's dm for this thin rod? Let's take a chunk of it. There's my dm. How could I get this into an integral that I could actually use? What's something we've done in almost every problem when we have this picture and I slice it up like this? What's one of the things we do? Say again?
State how far away from the axis.
Yeah, we describe the distance to the chunk. In this case, what's a good name for that? X, because we're using the coordinate system shown. And what's a good name for this thickness? So what's dm? Nope. That would have, no, dm, x dx would be units of meters squared. That doesn't make sense that way. So try again. Lambda. Because this is kilograms per meter times meter. And so that's how I like to check those units when I'm plugging in something before I waste a lot of time. Good idea? Okay. The units look good. What are my limits for this particular problem? What is it?
0 to L.
0 to L. Sometimes it's negative L over 2 to positive L over 2. Sometimes it's, all kinds of things. In this problem, the smallest value of x, or the leftmost value of x, is 0. The rightmost value of x is L. Well, in this case, we got this thing easy, right? Always check both limits. In this case, the 0 limit drops, not in every problem. What are we trying to find? Alpha. Can we get alpha? Yeah, so if you've ever wondered, how are we supposed to get these constants in the density? Well, you could put something on a scale, and if you know it varies nonlinearly, you could say, well, I'm going to assume it varies in this fashion and figure out the constant. You could do that same thing in your code, right? Play with the constant until you get the right total mass. Okay. What are the units? How could I check this answer? What units did I get? If I plug that in up here, does that have correct units? What are the units of lambda supposed to be? Kilograms per meter, that's meters squared. Is that going to make the equation have the correct units? We're good. I'm feeling happy. Okay. Now get the moment of inertia about the y-axis. Now, believe it or not, there's a standard symbol for this. It's IYY. That comes from the fact that you could do matrices for these, and I'm not going to say any more about it. I'll tell you on the break if you're curious. I could draw you a rotation matrix later, and a moment of inertia matrix later. It's called a rank 2 tensor. Okay. Now in this case, I forgot what the problem was. Where are we? Trying to get the moment of inertia. Okay. I want to go about the y-axis. I slice it parallel to the y-axis. Oh, we've already done that. So if I want the moment of inertia about the y-axis, my radius becomes x. This is very different than center of mass, right? It's like, look, 90 degrees. dm was that's dm. After I finish the problem, I could plug in what alpha is, and I could get this in terms of the total mass and total length. Let's do it. Oh, what are my limits? I forget. 0 to L. So we're going to get, what is this? I'm getting kind of lazy and running out of board space. That's going to be x to the 5th over 5. The zero limit's going to drop. I don't like doing that, but I'm running out of room. Alpha is well, out of all that, what do you get? 3/5 m L squared. Does it have the right units? It should always be, for a moment of inertia, some number times mass times a distance squared. Does this meet our expectations? We expected it should be greater than 1/3. Is this greater than 1/3?
Yes.
Yeah. Now, sometimes it's not obvious. What could you do if you were trying to compare two fractions to see which one's bigger? Put them into a calculator and look at it as a decimal. So sometimes it helps. We expect IYY greater than 0.333 mL squared. Got IYY equals 0.6. Right? It's a lot easier to compare decimals than fractions, so don't overthink it because you get tired sometimes. There's no shame in punching it into the calculator and double checking. What do you think? Good? There is a last note I wanted to make. In center of mass problems, this is subtle, so, oh, wait. So here we go. Listen to this carefully. In center of mass problems, you could choose whatever coordinate system you want. If I give you a non-uniform density, this function is linked to the coordinate system I gave you. So if you have non-uniform problems, whether that's center of mass or moment of inertia, if it's non-uniform and I give you a density, you could move the coordinate system, but you need to do a lot of math to fix up the density before you integrate. Basically what I'm saying is, if I give you a non-uniform density, don't change the coordinate system. Understood? Does that make any sense? All right, good enough. All right, that's non-uniform rods. All right, parallel axis theorem, page 62. I cannot stress this enough. It's crucial that you are an expert at page 62. Page 63, meh. Page 62, you must be perfect at it. Or near perfect. It's a very unforgiving thing to screw up. Let me draw this too. Draw this for you. Let's say we have some point. This is used in so many problems to avoid calculus. We're going to learn this trick extremely well so we can avoid doing calculus. Let's say we have some weird plate here. Okay, so that's supposed to be a plate. I don't know if it's uniform or non-uniform. But somehow, let's say I'm rotating it about this axis right here. And let's say its center of mass is right there. Okay. I'm going to put an axis through the center of mass. You guys use this symbol that looks like 11 to say parallel, 2 lines, that's parallel. I'm just going to write parallel. It may seem obvious, but if you want to use the parallel axis theorem, something must be true. The axes must be parallel. I know that seems crazy, but students screw this up all the frickin' time. To use parallel axis theorem, axes must be parallel. The main way students screw this up is you grab the wrong thing out of the table, right? If you look in the table, there's many different axes in there, and you grab one that looks like the right shape, but it doesn't have the right orientation. Okay, that's number one. Number two, it only works if one axis through center of mass. Another common mistake is people take 2 axes that are parallel to each other, but neither one goes through the center mass. You need these 2 things to be true. Enough said? If that is true, we get this beautiful formula. If the distance between the 2 axes is d, the moment of inertia about the parallel axis is the moment of inertia about the center of mass plus mass times d squared. Why is this such an important thing to learn? I'm going to give you a table where most of the axes are drawn through the center of mass. If I draw a problem where it's not through the center of mass, I expect you to grab the right thing out of the table and correctly add mass distance squared. Take a look at the table on page 59. Just look at the table on page 59. very often what I'm going to expect you to do is I'm going to draw some problem and we're going to rotate it about the edge of an object. This is the most common application. You rotate about the edge of the object. So you go into that table, grab the moment of inertia about the center, say for a disk or a sphere or whatever, and then you just add in md squared so you can get the correct moment of inertia. Does that make sense how we're going to use this? All right, let's go back and play with it. All right, ooh, 10.16. Let's do it. Am I on the right whiteboard? God, I hope so. Yes. Let's do 10.16. I'm going to go this way. Okay. 10.16. Uniform rod, mass L. Okay. We're going to rotate it about this axis. I'm told that this distance here is x. Right? What if you want to rotate this rod about some point that's not at the end? This is a very common application. Okay. Figure out the moment of inertia. Okay, help me out. Gee, I bet this is a good candidate for the parallel axis theorem. Do you agree? Otherwise, I wouldn't have just said it and done an example problem. So we know we're going to use the parallel axis theorem. Well, if I write that down really quick, oh, there it is. There it is. We've got our parallel axis theorem here. I want to use this. Is the axis shown going to be the purple one through the center mass or the green one parallel to the center mass? What does it look like? Is that axis through the center mass? No. So that means this needs to equal I center mass plus md squared. I'll get out of the way. Right? This is clearly not through the center. I know the length of this rod is L. What should I grab out of the table? Go look at the table and tell me which moment of inertia to grab. Why 112? What's your thought process? It's parallel. Is that sufficient?
It's not right at the edge.
Okay, so you're saying 1/3, and you're saying 1/12. Is that what's happening or
No, I'm
not?
saying the axis of rotation, it's not at the edge. It's like closer to the center. So
Exactly. Yeah, exactly. So you're right. It's 1/12. It's 1/12 because the 1/12 goes through the center and is parallel. That fits both criteria. You were right. You feeling good? It's not enough that it's parallel. I was hoping you would also say, and it goes through the center mass. That's what I was searching for. You good? Which is what you contributed, right? Good. So this needs to be 1/12 m L squared. Sorry, I'm getting sloppy. What was it? Capital M, lowercase m? Any m goes tonight. Axel Rose. All right. What's the distance I need? What is D?
Between X and this.
Want to just come up and point at it? That's probably easier to try.
The axis, that X, the distance
From here to where?
to the center.
Yes, that's D. Good. That made sense. Good way to do that.
L over 2 minus x.
And that distance is L over 2 minus x. I can tell you guys are going to do all right. So notice I was trying to trap you into thinking you could use 1/3 and just d equals x, and you saw through it. Good job. So, and then you got to remember to square it outside. You can't just square each term or just, yeah. So, yay. This is ugly, but we could probably clean it up a little bit. I do have a question for you. We could check the units. The units are good. Both terms have kilogram meter squared. Kilogram meter squared. What's another way you could check this? Give me special cases for the value of x. What's one special value of x, which would be really easy to check? If x equals 0, what should we get? 1/3. If x equals 0, you're all the way over here. Shouldn't you get 1/3? Well, let's check. If x equals 0, you see it? You got it. Feeling good? All right. You should do 10.18 at home. Why don't we try, I know it's not Halloween, but let's try 10.19. I'm tired of all these zombies. Let's get Dracula involved. In 10.19, Dracula takes break from sucking the blood. He sees this triangular plate. He says, using the dotted line axis from problem 10.13a, I know the moment of inertia was 1/6 ml squared. Remember we did that earlier? He telepathically communicates to you, I'm going to use the parallel axis theorem. I dotted should equal I solid plus ml squared. I'm going to kind of draw that up while you guys think about it. Read that question. I need to erase the board. Dracula drinking blood. Says go Bulldogs. It gets the center of the triangle here. So let's basically say if this side is S, and this is S over 2, if that helps. Put a little shading in here so it looks a little better. So you have the solid line axis and the dotted line axis. We know this one has I equals 1/6 ml squared. So I guess this side was L, not S. I apologize. Dracula says, I'm going to use I dotted equals I solid plus the mass times L over 2 quantity squared. Is that correct? Go Bulldogs. The garlic. Why is this wrong?
I
solid is in the center.
Exactly. Going halfway over is not the center mass of the triangle. This axis doesn't go through the center mass, not valid. Where is the center mass for a right triangle?
L over 3.
Yeah, it'd have to be right here somewhere, right? Not true. You need at least one of the axes to be at the center. Okay, let's try this. Try 10.20. Frankenstein's here. We got Frankenstein. Why am I writing Frank? Frankenstein. Let's just call him Frank. Okay, we've got a disk. Okay, and Frank says, the distance here is r, right? So can I just plug in mr squared? Frank says it equals 3/2 mr squared. My claim is Frank is wrong. My claim is Frank is full of it. This is not true. What is wrong with this? My physics teacher says this is total crap, but whatever. What's wrong with this one? I'll give you a hint. Look at the table. Look at the pictures.
It's 1/4.
Yeah, this is the moment of inertia about the center mass of a disk if the axis points this way. So this is the wrong axis orientation to use. The moment of inertia about this one is I equals 1/4 mr squared. That's what you should be plugging in right there. Not this silly 1/2. Bad. You see, I'm trying to show you the common mistakes students make. They grab the wrong thing out of the table, or they forget that one of the axes has to go through the center mass. Is that enough on that? You feel like you can try to get this most of the time? I'm not going to try to trip you up. It's just sometimes people forget and grab the wrong one. Page 63. I don't have time to cover it this semester, so I'm throwing it out. Sometimes I used to give an extra credit question about the perpendicular axis theorem. If you're into math, go ahead and check it out. If you're not, that's cool. Why don't we look at page 64 right now and look at a summary of how to deal with moment of inertia? Page 64. Everybody got their workbook on page 64. Let's summarize what we did today. Here, I'll give you this too. Well, actually, I'm gonna have trouble. Maybe look at his book. All right. Identify the axis location and orientation. I'll write it on the board. Not a space. All right. Skim that page while I'm erasing. How about that? I just want this to be rock solid for you. You've got to be automatic on this stuff. Otherwise, everything that follows is wrong. you have to pay attention to the axis orientation and location. That's critical. If you screw that up, you grab the wrong formula, you're done. Hopefully, you can add or subtract using I total equals I1 plus I2 plus I3. Split it into parts and just add them up. But remember, when you're doing that, you have to look carefully at each part and make sure you have the axis and correct for each part. So that's basically grabbing things out of the table. 3. Can you use the parallel axis theorem instead? Remember, you need parallel axes. One must be through center mass in correct orientation. Or ignore for this class this semester. If you're watching this YouTube on a future semester, talk to me in real life. Okay. We're not going to use but basically, if you were trying to be a professional, you would try to use the perpendicular axis theorem. And then if all else fails, basically for us, if non-uniform rod, and again, for future semesters, you better check with me. If you're watching this video later. We did some integrals. So it's funny, right? Integrals take the most time, and we try to avoid them at all costs, but at some point, you got to do them every once in a while, right? That's basically what we try to do. Does that kind of make sense, or any questions about the strategy for getting moment of inertia? Bored out of your mind or no? It's been like this is kind of like vectors, right? Where you have to do it, but it's just kind of math all day. Let's go look below there. Insight. Do you see the insight? Let's read that insight or tips, whatever you want to call it. Mass close to axis. I is small. Now, small is a relative term, right? Okay. Small I implies easy to change rotational state. You could say easy to alpha. Does that make sense? Where alpha is angularly accelerate, right? Changing the rotation rate is the same thing as angular acceleration. Does that make any sense? Right? If you have a small mass, it's easy to change your velocity. It's easy to accelerate. If you have a small I, it's easy to change your omega. I didn't say this yet, but here's a neat tip. You can see this from the parallel axis theorem, but here's a neat tip. The moment of inertia about the center of mass is always smaller than any parallel axis. Right? Look at the parallel axis there. If you go away from the center of mass, you increase the moment of inertia. That's kind of a cool thing. I'll forget the fourth bullet, but for planar objects, the moment out of the plane is always greater than the moments of the inertia in the plane. And I don't really want to go into that, but that's for the perpendicular axis there. At home, if you really want to know this problem, look at 10.23 and a half and 10.23 3/4 at the bottom of page 64. If you could do those, you're in good shape. And then make sure you can do non-uniform rods. If you like baseball, 10.24 asks about choking up on a bat. That's kind of fun. All right, whatever. There's lots of fun. You can do this. Oh my gosh. You can tell it just keeps going for pages and pages. Oh my gosh. If you're a freak and you really like math, check out page 67 and have fun with that. Oh my gosh, it keeps going for pages and pages. 67, I love moment of inertia. I'm going to stop talking about it. Okay, I love it. I know you love it. You secretly just don't know it yet. Let's go to page 69. We got 10 minutes. Okay. I want to foreshadow tomorrow's lab. Tomorrow's lab is going to be half lab, half lecture. And so, but it's going to be all fun. Don't worry. Oh, yeah.
First, the lab or lecture.
It's going to be mixed.
Okay.
But probably the lecture, most of the lecture will come first. And so I may give you some problems you could do in advance to kind of make sure you can get your data in a timely manner. I know moment of inertia is a boring topic sometimes, but if you can get into the math, you'll love it. Torque, page 69. Talking about torque. The equation you're going to see is tau. That's a tau, the Greek letter tau. What are the units for radius? Meters. What are the units for force? I was going to say newtons, but okay, you're right. Now, one of the annoying parts is the units we usually say are Newton meters. But has anyone ever used a torque wrench? Sometimes they're used in units of. And then Dom, help me out. S or no S? There's no S, right? So you're supposed to say foot pound. But people say foot pounds all the time. I don't care, but engineers probably do, right? I think there's no S on that. And you can talk to Dom about the origins of that. I don't know why Dom does. All right. But so I kind of like thinking in foot pound, right? You got foot pounds here for the reason of it gets the order right in the cross product. So all that vector crap we did at the beginning is finally going to come true. The main thing that we're going to learn is just like we had sum of forces equals MA, in rotation land, we're going to say the sum of torques equals I alpha. And it turns out as engineers, sometimes they're going to use the word moment, which we could talk about statistics and moments about the mean and things like that. The mathematical relationship is equivalent. So sometimes you'll hear engineers say sum of moments. I don't like that. I'm going to say sum of torques. Wow. I wrote a tau there for no good reason, but whatever. I like to say sum of torques. You could say either one. And if you're an engineer, you better say the first one. Okay? Don't make me happy. Make your engineering boss happy. Okay? Now in this case, imagine we have a rod here. And let's say there's a pivot point. There's always a pivot point or an axis. So if you're wondering what I mean by an axis, right? The axis would point out of the page, but it's a pivot point. So right there's the pivot point. Okay. And there's some applied force. There's my applied force. So maybe to keep the color coding consistent, I'll change this to blue. It's crucial that we understand what R means in this equation. R is a vector from something to something, right? That's what an R vector is. Here, it's from the pivot or axis to point where force applied. I'll get out of the way. Sorry, I'm right in the way. That is crucial. These are vectors. If you screw up a minus sign on one term, you screw up the whole problem and cry. Okay, we do not want to do that. In this problem, I'm from the pivot all right, just trying to make sure it's visible. Okay, it's that way. That is the R vector. From the pivot to the point where the force is applied. So maybe I'll draw that in red up here. Now, in theory, I'm done talking. We could say I've covered this chapter. Yeah, right? There's so many tricks when you do torque and cross products. We need to do a lot of practice on this. You could see I have shown you 4 different methods for calculating the torque in practice. 4 methods are common. And I wish I didn't have to say all these, but all of them are used at different times. Now, to be fair, one method rules them all. You can always do the first one and describe the vectors and write them out. This always works. But there are shortcuts that are sometimes extremely useful. So this one always works. You can use the wheel of pain. You got a cross product. It's just a simple. We did problems like this in chapter 3, if you remember. I just said, here's an R vector, here's a force vector, do the cross product. Piece of cake. We could get the magnitude and use a right hand rule. Remember that? So I could say, line my fingers up with the first term. I'll use right hand rule for direction. Look at this one. R goes to F, thumb points out of the page. Which way is my torque for this problem? Out of the page. What does that mean? It means the axis is out of the page and the thing is actually going to twist counterclockwise. Right? Remember we were talking about a rotation axis? The torque tells you the direction that it will rotate, about which axis it will rotate. Cool? I don't know, whatever. You could use for the magnitude, what did I say? R perp? R perp. So this is the perpendicular symbol. That means perpendicular. You say this R perp. Or R perpendicular. Sometimes, maybe you've heard this before, that's called a lever arm. But I generally call it R perp. Dom, do you call it R perp? Or do you just call it lever arm? Or what do you call it? Do you use this term or not?
Use D.
Okay, whatever, yeah. But it's the lever arm,
Perpendicular distance.
perpendicular distance. So now check this out. This is shown for you on figure, what did I say? Middle figure at right. Method 3. Look at page 60, page 69, method 3. The idea is that, let me label this better. If this is R, this would be R perp. The perpendicular distance to a line that runs through the force, imaginary and infinite direction. We're going to call that this line that runs through space infinitely in all directions is called the line of action. So if you have a force applied to an object, you can draw a line infinitely long in any direction until you could draw a perpendicular line. This is a perpendicular bisector to that line. It bisects this line, which is infinitely long in both directions, perpendicular. Okay, so you could figure out this distance. In some problems, that's actually really easy. That's the way to go a lot of times. Or, I know this is going to seem a little crazy here. Actually, I'm going to draw this way now. Typically, in this portion of the class, we draw our force components a little bit differently. This would be a force parallel, and this would be a force perpendicular. And it turns out you could also write this last one, and then I'll leave it at this and call it a day. You could say the magnitude of the torque is actually the full radius times the perpendicular force. And I don't know if this makes any sense to you, but imagine if you pulled on this rod this way. Right, if I was pulling this way, it wouldn't twist. The parallel component of the force should not cause it to twist. We're going to pick up here next time, but you could see that there's a lot to do here. So you should probably skim over this page and maybe read a book or something before tomorrow's lab. We're going to do tomorrow in lecture and lab. I know it's time to go, and I apologize. We're going to work on, basically the next few pages here, including, we're going to get all the way up to rotation. So basically page 73 and page 75 are what we're going to talk about in lab tomorrow, page 73 and 75. So we're going to be doing those problems tomorrow in class. We'll go over it then. So yeah, if you have time, read as much as you can. Let's call that good. Woo, I'm tired.